Recognizing the law of conservation of mass. I can relate the law of conservation of mass due to chemical reactions. Starter. In which investigation is it least likely that the liquids reacted chemically? So here are the scientists' observations and your investigations. So let's read those. So in investigation 1, the temperature of the combined liquids increased and a solid substance formed. So if you have an increase in temperature, that is a chemical change, because any change in temperature is evident of a chemical reaction. A solid substance formed, this could be a precipitation forming, which is another evidence of a chemical reaction. So in investigation 1, it is evident that a chemical reaction took place. Investigation 2, the temperature of the combined liquids decreased and bubbles formed. So again, you have a temperature change indicating a chemical reaction. Bubbles forming are evidence of a gas production. So investigation 2 is also a chemical reaction. Investigation 3, one liquid settled to the bottom of the beaker and the other liquid rose to the top. Now, this is not evidence of a chemical reaction. Rising and sinking or floating and sinking are not evidences of a chemical reaction. So this would be the least likely that the substance reacted chemically. The combined liquids turned from a clear to a bright blue. Now, this is a color change, so investigation 4 is evidence of a chemical reaction. In which investigation is it least likely that the liquids reacted chemically? That's in investigation 3, where there are no evidences of a chemical reaction. The law of conservation of mass. Matter is neither created or destroyed in ordinary chemical and physical changes. You must start and end with the same amount. So for an example, if we had logs that weighed 30 kilograms plus fire, which weighed 1 kilogram, this reaction would produce these products, ashes and smoke. And this would have the same mass, your ashes and your smoke would have the same mass as your log and fire. So the mass total here is 31 kilograms, where your ashes and smoke also would equal 31 kilograms, because matter is not created or destroyed. When a reaction occurs, elements rearrange and form new products, new substances. Law of conservation of mass. The law of conservation of mass states that matter is neither created or destroyed in ordinary physical and chemical changes. This law means that a chemical equation must show the same numbers and kinds of atoms on both sides of the arrow. The reactants and the products must contain the same number of atoms of each element. So up here we have our reactants to the left, and then we have our arrow, and then we have our product. When these elements react, they rearrange and form new products. So remember, your reactants, arrow, product. According to the law of conservation of mass, the reactants must equal the products. They must show the same kinds of atoms on both sides of the arrow.
The law of conservation of matter states that matter cannot be created nor destroyed, only transformed. The notion of a balanced equation is based on this principle. This means that the elements and the number of atoms of each element represented on the left side of the equation must also be represented on the right side. Take, for example, this equation. 2 hydrogen gas molecules, H2, are added to oxygen gas, O2. The product is 2 water molecules, H2O. Hydrogen and oxygen are reactants. The law of conservation of matter demands that both elements be represented in the product and that each element have the same number of atoms on the right side and on the left side. Hydrogen and oxygen are represented on the right side. Now let us count atoms. On the left side, hydrogen has a subscript of 2, meaning there are 2 atoms per molecule. There is a coefficient of 2, meaning there are 2 molecules of hydrogen. Multiplying through, we find a total of 4 hydrogen atoms on the left side. There are 2 atoms of oxygen on the left side. On the right side, there are 2 molecules of water, each containing 2 atoms of hydrogen for a total of 4 hydrogen atoms. There is 1 atom of oxygen in each molecule of water on the right side, for a total of 2 oxygen atoms. There are 4 hydrogen atoms on the left side of the equation and 4 hydrogen atoms on the right side of the equation. The hydrogen atoms balance. There are 2 oxygen atoms on the left side of the equation and 2 oxygen atoms on the right side of the equation. The oxygen atoms balance. The law of conservation of matter has been supported.
For an example, does the equation follow the law of conservation of mass? We're going to use bingo chips to help determine if the equation follows the law. Drag the bingo chips to count the number of atoms in the equation and then highlight yes or no. Justify your answer. Okay, so I'm going to look at the reactant side. These are your reactants, arrow product. If it helps, we can write that abbreviation RAP, RAP. Okay, let's look at our reactant side and see if this follows the law of conservation of mass with the product side. So here I have 1 atom of sodium and I have 2 chlorine atoms. Here in my products, I have 1 sodium atom and 1 chlorine atom. So this does not relate to the law of conservation of mass because my chlorine atoms do not equal. If I have 2 in my reactants, I must have 2 chlorine in my products. Does the equation follow the law of conservation of mass? So let's look at this chemical equation and do it together. First, let's count our atoms. So here I have a coefficient of 2, meaning I have 2 molecules of sodium. So I have 2 here. And then I have a coefficient in front of H2O, and then a subscript of 2 for hydrogen. So coefficient times subscript here would give me 4 hydrogens. And then I would take that coefficient and multiply it by oxygen subscript, which is a 1. So 2 times 1 would give me 2 oxygen atoms. Okay, so let me drag and drop my bingo chips. So I want to represent 2 nitrogen atoms. I'm sorry, 2 sodium atoms. So here are my 2 sodium atoms, and then I need 2 times 2 would give me 4 hydrogens. And then I have to represent my oxygen atoms. So 2 times 1 oxygen would give me 2 oxygen atoms. Okay, so this is what I have on my reactant side of the equation. Now I'm going to look at my products. So let's count atoms again. So I have a coefficient and no subscript after sodium. So I take that coefficient and multiply it by sodium subscript. 2 times 1 would give me 2 sodium atoms. And then I would take that coefficient and multiply it by oxygen subscript of a 1. 2 times 1 would give me 2 oxygen atoms. And then for my hydrogens, I have 2 times 1 hydrogen would give me 2 hydrogen atoms. So let's represent that. So I'm going to need 2 sodium atoms. And then I need 2 oxygen atoms. And then I need 2 hydrogen atoms. Okay, and then I have 2 hydrogen atoms over here. Okay, and now I'm going to answer the question that does this chemical equation follow the law of conservation of mass? Do I have the same number of elements and elements in my reactants as I do in my product? Okay, so we can see visually that you have 2 sodium in your reactants, 2 sodium in your product. You have 4 hydrogen atoms in your reactants and 4 hydrogen atoms in your products. You have 2 oxygen atoms in your reactant and you have 2 oxygen atoms in your products. So I'm going to highlight, yes, this follows the law of conservation of mass. And to highlight, you would go over to this little pen and select your color. Okay, and then you can give a justification. You can say the elements and the number of atoms of elements are the same in the reactants as they are in the products. Okay, I'm going to bring you to the next 2 slides, and you're going to do the same here. So we're going to look at our reactant arrow product and see if this follows the law of conservation of mass. So let's count our atoms. So I have a subscript of a 2 for my iron. So I'm going to bring over 2 iron atoms. And then looking at my oxygen, I have a subscript of a 3, so I can bring over 3 bingo chips to represent 3 atoms. And then in my reactant side, there is a plus sign, but that's still your reactants, okay, because this is one substance reacting with another substance. So I see 1 carbon here, and I see 1 oxygen atom there. Okay, so these are my bingo chips for my reactants, and now they're going to react, rearrange, and form a product. Now let's see if this follows the law of conservation of mass. So for my iron, I only see 1 atom, that one that I'm looking at because there's no subscript, plus 1 atom of carbon, there's no subscript after carbon. And then I have a subscript of a 2 for my oxygen, so I need 2 oxygen atoms there. So I'm going to look at my reactants and I'm going to look at my products. Does this follow the law of conservation of mass? Do I have the same elements and number of atoms of that element in my reactant as I do in my product? And you can see right from your iron atoms in the beginning you don't. You have 2 iron atoms here and 1 here. So this does not follow the law of conservation of mass. And you could also see that for your oxygen atoms because you have 3 here and then 1 here for 4 in your reactants and 2 in your products. Okay, and our last chemical equation to see if it follows the law of conservation of mass. So here are my reactants. I have 1 carbon atom. This has no subscript, so it's just 1, that one that I see. And then here after iron, I see a subscript of a 2, so I have 2 iron atoms. And then my oxygen subscript is a 3, so I have 3 oxygen atoms. These are my reactants. When they react, they're going to rearrange and form a new substance. Okay, so let's see if this follows the law of conservation of mass. I see I see 1 carbon and 1 oxygen atom. This will need to be a capital, plus 1 iron atom. So does this follow the law of conservation of mass? Do I have the same elements and the number of atoms of those elements in my reactant as I do in my product? No, I don't. Okay, so I'm going to highlight no, and I'm going to give a justification. So yes, my carbons are equal, but then when I go to my oxygen, I only have 1 oxygen here, but 3 oxygen atoms in my reactants. And then if I look at my iron atoms, I have 1 in my product and 2 in my reactants. So that would be a perfect justification. Let's go to our analysis questions. So what does the law of conservation of mass state? The law of conservation of mass states that matter cannot be created or destroyed. Whatever the mass is in your reactants must equal the mass in your product. So that is the same elements and the number of those elements in your reactants as in your products. If an equation follows the law of conservation of mass, then you have the same elements and number of atoms of those elements in your reactants as you do in your products.